Hello and welcome all of you to this session of Heat Power Engineering. Today we shall start our discussion on the first law of thermodynamics for the closed systems. So previously, while discussing about the concepts of the systems, we had seen that the systems can be classified into three broad categories. The first one was the closed systems. Closed system means it permits energy transfer but no mass transfer. That means it is a system whose identity remains fixed. So we'll be observing how the energy transfer process takes place for the uh, closed systems. Okay, so we will be trying to understand the first law of thermodynamics for the closed systems. So let us see what are the lecture objectives. So we will analyze the first law of thermodynamics for closed systems. We will analyze the terms which is related with this state equation, and then we will start analyzing the distinct natures of energy. We will observe that in the statement of the first law of thermodynamics, energy is present in two distinct categories. So we will see and we will observe what are the distinct nature of energy which is summarized in this first law of thermodynamics statement. So that is a very important concept which you must understand very clearly and properly, because it will help you understand lots of things afterwards. And then in the previous lecture we had already told that we will be observing the characteristics of the specific heats from the thermodynamic point of view. Previously we had seen from the heat transfer point of view. So today we will be observing the specific heats and how it can be deduced from the point of view of thermodynamics. And then with these concepts we'll solve a numerical problem which I believe will broaden your senses about the uh, first law of thermodynamics. So let us see how we can start our discussion on the uh, first law of thermodynamics. Okay, so let us see the lecture.
So, as you can see, there is an adiabatic vessel which is considered to be a closed system. That means heat cannot be transferred into or out of the system. So we have considered fluid system here. The water is our general fluid. So now what Joule did, he gave an work input of W into the fluid system by the means of a paddle wheel system. Okay, so by the means of stirring work, there is a certain amount of work input into the system. So what was the effect of this work input? The temperature of the fluid system, which was at T1 degree Celsius, it got increased to T2 degree Celsius. Okay, so there was generation of thermal energy within the fluid system which helped to increase the temperature from T1 degree Celsius to T2 degree Celsius. Now this temperature change can be easily recorded by the means of a thermometer, which was also incorporated into the fluid system. Okay, so the temperature has been changed, but the volume and the pressure was constant throughout this process. Now if we want to plot the state changes, that means initially it was at T1 degree Celsius and after that it got changed to T2 degree Celsius. If you want to plot that, then we would require some thermodynamic coordinates. So let us assume x and y are the thermodynamic properties by which this process, this state change, can be expressed. So let us take this one as the state number 1 and this is as the state number 2. Now we can connect these two by a continuous line. Now one may argue that it is not an quasi-static process. How we can join this how we can join these two states by a quasi-static by a continuous line? So he is saying the perfectly right thing, because it is not a quasi-static process. It can't be joined by continuous line, but for the sake of simplicity I am joining these two states by a continuous line. The it will be much more precise if you join these two states by some dotted line. So let us do that. I will be trying to join these two lines by the means of dotted line. So now you can understand it doesn't refer to a continuous or quasi-static process. Okay, so this is a sharp difference you need to understand. So a process has been carried out where there is an work input W. We may refer this W as W1 to 2, which will be much more precise, and as it is indicating the change of states. Okay, so there is an work input W1 to 2 within the system. Now after that, what Joule did, he wanted to measure the temperature change by applying some amount of heat energy. So what he did, he took the same fluid system, he insulated the lateral sides. So let me just uh, draw this hatch line so that it can be shown as insulated. So he used a system where the lateral sides were insulated. Okay, and he connected the fluid system with a hot body. The fluid system has had a temperature of T1 degree Celsius, and the hot body had a temperature much higher than T1 degree Celsius. So heat transfer took place and he recorded the temperature change. So he recorded the magnitude of heat transfer which is required to change the same temperature level. That means for T1 degree Celsius to T2 degree Celsius, how much heat is required? Okay, so the temperature already was found from the data of thermometer. So he performed the experiment by placing a hot body near the fluid system so that heat transfer can take place, and he recorded the exactly same temperature change and measured the magnitude of the heat transfer. Okay, now he found that the heat transferred was exactly equal to the work transfer. Okay, now there is a little bit of confusion and little bit of extra information I need to provide here, but I will give it later. Okay, now so this part was done. So he found that the heat transferred to cause the same temperature is exactly equal to the work transfer which is causing the same temperature. So this was the basic observation which he found from this experiment. Now what he did, he carried on this experiment in a different way. He after the fluid had changed its states from T1 to T2, that means the temperature was increased from T1 degree Celsius to T2 degree Celsius. He placed this fluid system with a surroundings which is of cold water. Okay, so this system had a temperature of T2 degree Celsius, and he wanted to see what is the amount of heat transfer required to change this T2 into T1 degree Celsius. So heat was flowing from this fluid system to the cold water. So you can see, you can write this as the system B and this fluid as our system A. Now it is easily understandable that this A or this fluid system had higher temperature, whereas the surroundings to this fluid system, the cooled water had lower temperature. So heat started flowing from the fluid system to this cooling water. Okay, so he recorded the amount of heat transfer which is required to cause the same temperature difference. That means after some amount of heat transfer, he found that the temperature has been changed from T2 to T1. Okay, so he measured the value of the heat transfer. He found that it was Q1 to 2. We are taking this as Q1 to 2. Now what is the relation he found? He found that the amount of heat which is being transferred to cause the same temperature difference is exactly equal to the work transfer. Now in the previous days, heat was considered to be an invisible fluid which flows from a body which has higher calorie to a different body which has obviously lower calorie. Heat and work was expressed in two different units. So what he found? He found that uh, heat, the work transfer, this W12 is proportional to the heat transfer. So what he did, he wrote this equation in a different way. He incorporated a proportionality constant which we know as Joule's equivalent or mechanical equivalent of heat. But after this experiment, it is easily understandable that heat and energy are heat and work are the different forms of the same entity, which is energy. So heat and work transfer would obviously have the same units. So after this experiment, he found that this J is equal to 1. So the equation became W1 to 2 is equal to Q1 to 2. Okay, that means we can write this equation in a little bit different way. Like we can write for the whole cycle, W, that means work transfer for the whole transfer is equal to heat transfer for this whole cycle. Okay, so since these two processes, the work transfer and the heat transfer, are constituting a thermodynamic cycle, we can easily say that W1 to 2 is equal to Q1 to 2. Okay, so in form of cyclic integral, so in the integral format, it can be written as cyclic integral of dw is equal to cyclic integral of dq. That means heat transferred through the cycle is equal to the work transfer for this thermodynamic cycle. Okay, so this was the basic observation of this Joule's experiment. Okay, so the basic point which we understand that energy is conserved. So we can always state first law of thermodynamics as the conservation of energy principle. That means you are providing an input of W1 to 2, that was the work input, by the means of stirring work or paddle wheel work, and you get a change of temperature or a generation of thermal energy which is equal to dq. So the so this is valid for all the processes. Okay, so energy, that means heat and work, will be always conserved when a closed system is undergoing a cycle. So the statement of the first law is nothing but that. Okay, I hope I have uh, made it clear to you. So first law of thermodynamics is exactly synonymous to the conservation of energy. But since when thermodynamics deals with work and heat transfer much more, we can say that the amount of work transfer through the thermodynamic cycle for the closed system will be equal to the amount of work transferred through the thermodynamic system uh, for this closed system. Okay, so let us move on to the next part when we'll be observing the first law of thermodynamics for again a closed system, but we'll see that there is a change of state. Okay, so this for the second part we'll see that this is not the processes are not occurring in a thermodynamic cycle. Okay, then how does first law of thermodynamics is applied there? So let us see that. So as you can see here, a system, there is a system present over here, which is given by this boundary, the circular boundary. And when this system undergoes a change of state during which both work uh, work and heat transfers are involved, the net energy is stored within the system itself. So this stored energy is nothing but the energy in storage format, which we have been discussing for the long time. Okay, so if you see this diagram, if you follow this diagram, you will see that there is heat transfer of Q into the system. Okay, so there is heat transfer of Q into the system, and you can see that there is W work output from the system. So we can see that we can easily do the energy balance. So Q is the input and W is output. So the difference between these two is stored in the format of internal energy, which we write as del U. So Q minus W is equal to del U. So now we can see there are this Q and W are the two different forms of energy. That means they are the energy in transit forms, and this one is energy in storage. So two different and distinct forms of energy have been collaborated here in the first law of thermodynamics statement. Okay, so um, it must be mentioned that this del U, or the change of internal energy, is because of the change of state. Okay, so and we can always say that energy is always conserved. So it is quite evident that first law of thermodynamics is nothing but the conservation of energy principle. So now talking about del U, del U is the change of energy because of the change of state. Now it implies that energy has a energy or internal energy has a definite value for a definite state. Now when a property now it is now you know that a property is something which has a definite value at a definite state. So we can state that, we can mention that this del U is nothing but a state variable or a point function or a property of the system. So this del U is nothing but a property of the system. Okay, so we will just move on to the next part, where I will show you how we can um, give assign this del U as a property. Okay, how we can mention this change of internal energy as a property. So this is a property, this is obviously a point function, and this is an state variable. Okay, so it depends on the state. That is what I have mentioned here. It has a definite value at a definite state. So point function, property, or state variable, you can call it by many names. Okay, so let us see how does it can be stated as a property. How can we state this internal energy as a property? Okay, so here you can see. So let us consider a system. So these are the coordinates, these are the thermodynamic coordinates x and y. The system has changed its state from 1 to 2 via a path A, and the system is returning again to its initial condition via a path B. Okay, so this path A and path B together are constituting a thermodynamic cycle. Again, we can also say that this system can come back to its initial position via this C path. So this A and C together also creates a thermodynamic cycle. So we can say for path A, for the path A, according to the principle of first law of thermodynamics, we can easily say we are assuming that QA is the amount of heat transfer. So for that, del UA is the change of internal energy and WA is the work done. So for path B, it will be something similar. QB is equal to del UB plus WB. Okay. Now, as we can see here, A and B, these two paths have constituted a thermodynamic cycle. Now, we can apply the first law of thermodynamics for a thermodynamic cycle. So that states that, if you remember, W, so the summation of all work transfer for this thermodynamic cycle is equal to the all heat transfers for this thermodynamic cycle. Now, so you can write QA plus QB, which is equal to WA minus WB. I'm sorry, it will be WA plus WB. Okay, the summation of all work transfers is equal to the summation of all heat transfer, and this is the uh, first law of thermodynamics when there is a change of state. So there is a minor difference, you must understand it. In the first case, here there is a change of state, and here it is, this process is carried by the help of a thermodynamic cycle. So these are the two differences. Okay, now QA minus WA would be obviously del UA. So just from this equation, I'm just writing this fact: QA minus WA is equal to minus of QB minus WB. Okay, so QA minus WA is equal to del UA. Okay, so this is the change of internal energy for the thermodynamic path A, and this is the change of internal energy for the thermodynamic path B. That means when the system follows this path B, this is the change of internal energy. But you must remember, internal energy means the change of energy for the two different states. Okay, so it doesn't depend on the path. Okay, but this, as this system follows this path, I am using this word B here. Okay, now for if we apply the same law for path C, then it is quite evident and simple to say that it will be del U C plus WC. And again, you can see both A and C together have constituted a thermodynamic cycle. So we can write QA minus WA is equal to minus of Q, it will be C, QC minus WC. So it is quite evident. Okay, so it will be equal to minus, so I hope this is Q. I'm sorry if it is very hard to understand. So it will be change of internal energy for the path C, or we can write del UA here. So if you look into these two equations, you can say that del UB is equal to del UC. Now see, for this change of internal energy, the system has followed a path B, and for this change del UC, the system has followed a different path C. Okay, so it is now can you say it? Now it is easily understandable that the change of internal energy doesn't depend on the paths, it depends on the state. So if, as both B and C had the same initial and final states, the change of internal energy for these two paths was exactly same. Okay, so change of internal energy is independent of the path the system has followed. It is only the difference of energy stored within the system for the definite states. So I have uh, previously I have also mentioned that this internal energy is nothing but a property or a state variable. So it also, now I have just proved that. Okay, so energy is a property of the state, it is a state variable, and it is a point function. Okay, now let us see what are the characteristics of the internal energy. That means how do we identify the various modes of internal energy which comes into practice, regular practice. So before moving on to the discussions of the various forms of stored or internal energy, I would like to mention you that we have just expressed internal energy as a property of the system. So whenever a system is undergoing a process via a thermodynamic cycle, it is quite easy to understand that the change of internal energy would be zero, since in a thermodynamic cycle the initial and the final states are exactly the same one. The change of internal energy would be always zero. So let us take an example so you can understand it very easily. So let us assume that this is your xy coordinates. So we have assumed x as the intensive property and y as the extensive property. Okay, so the system is changing its states from 1 to 2 via path a, and then returning back to the initial position 1 via path b. Now for the path a, the change of internal energy we have to calculate. Okay, so we are assuming that the system has u1 as the internal energy for the state 1, u2 as the internal energy for the state 2. Now for the path a, the internal energy change would be u2 minus u1, but for path b, the change would be u1 minus u2. So if we write summation of du, or we can also write closed integral of du. So the summation and this closed integral, they are mathematically the same thing, so you can see that it becomes 0. So the change of any thermodynamic property for a thermodynamic cycle would be always 0, because the initial and the final states are the same for any thermodynamic cycle. So since internal energy is also a thermodynamic property, there is no exception here. Okay, now we'll be moving on to the discussions of various forms of stored or internal energy. Okay, now energy in storage or internal energy, which we are trying to discuss, can be understood from two different viewpoints. Okay, one is the macroscopic view and the second one is the microscopic viewpoint. Okay, now any system which is moving or which is at rest does have ke and pe to help for the motion and to maintain at the position of rest. Okay, so macroscopic mode means the Ke and P, that is kinetic energy and potential energy, associated with it when the system is in a state of motion or rest. Okay, but in case of microscopic mode, we need to understand the molecular phenomena from a quite interesting point of view. So we know that the molecules are in a random motion for the gas, if we consider, and they are colliding with each other. So we can observe different forms of energy like translational kinetic energy. So translational kinetic energy. Okay, we can also observe translational Ke. We can also observe rotational Ke. We can also observe vibrational energy, and we can also observe chemical energy. So rotational Ke, vibrational energy, and chemical energy. Okay, so internal energy is the summation of all these different modes of energy which is available. Now, so we have understood the various forms of stored energy. So you have to remember that internal energy, when we are talking about internal energy, it refers to the summation of all these separate molecular level energies. Okay, so it involves translation and kinetic energy, it involves rotational kinetic energy, it involves vibrational energy, and it also involves chemical energy. For different matters or different molecules, we also can find electronic energy and other different modes of energy also. So but the point is, whenever we are trying to mention internal energy or intermolecular energy, which is entirely dependent on temperature, this refers to the summation of all the different modes of energy which are available in the molecular motion. Okay, now since we have understood all of this, let us try to write this equation in a different way. So this is the integral way or the differential way of, that means we are using little bit of calculus here. This this cut represents the imperfect differential, which I have already mentioned. Now if in a system, if there is no other mode of work present except PDV or displacement work, then we know that this dW can be written as PDV. We have already done some numerical regarding this, and we have discussed it in a much detailed fashion. So in the system which is not performing any other work transfer except piston displacement work, we can write this formula. So the first law of thermodynamics, when there is no other mode of work involved other than PDV or displacement work, the formula can be changed. So in algebraic way, we can write this: Q is equal to del U plus integration of PDV. Okay, so this refers to the wholesome change. Okay, so I had discussed the different modes of energy and how the first law of thermodynamics can be modified according to the various kinds of work transfer involved. Now if there is other kind of work transfer involved, then we just need to add up. Suppose there is paddle wheel work. Okay, so we would we would need to write this mgz or integration of t d theta here, so that this work transfer can be also included in this formula. So whenever this dw is mentioned, that means it refers to the summation of all the work transfer which is going on throughout the system. So after understanding these properties and this, after having this discussion, we will be moving on to discuss a new thermodynamic property which we call as enthalpy. So let us see what enthalpy is. So just few moments earlier, we have mentioned that if there is no work transfer except PDV or displacement work, the first law can be written as accordingly to this formula: dq is equal to du plus pdv. Okay, so now if we rewrite this equation for the constant pressure, then we would like to mention that we can add up an vdp here. Since the pressure is constant, this dp will be obviously 0, so we are adding up a 0, and this doesn't change the expression. So after that we can rewrite this equation du plus d of pv. So ultimately we can write this equation in the format of u plus pv, u plus pv, and we define the heat transferred at constant pressure as a new property which we call as enthalpy. So enthalpy is a property which is defined by the heat transferred at constant pressure. So we are talking about specific enthalpy here, which is H is equal to U plus PV. So this has the unit of kilojoule per kg or joule per kg, whatever you may like to call. So this is the specific enthalpy, and for total and enthalpy calculation we need to write U plus PV. So obviously this capital letter indicates the total properties, that means it is for the total mass, and the specific enthalpy refers to the properties which is for the per unit mass properties. Okay, so enthalpy is nothing but the summation of U plus PV. Now for ideal gases we know that PV is equal to RT. Since this internal energy is also a function of temperature only, and obviously it is quite evident that R is a constant itself and is the left T is left here. So this enthalpy becomes a function of temperature also. So whenever you will see it is given to you, it is quite easily understandable that enthalpy will be always a function of temperature. Okay, so I hope that you have understood the concept of enthalpy. Enthalpy is nothing but the heat transferred when the pressure is kept constant. That is as simple as it is. It is nothing but the heat transfer, but there is a specification about the process here. The pressure have to be kept constant. So with this understanding we will go on to define specific heat at constant volume and specific heat at constant pressure. Okay, so simply we can write Cv is equal to the partial derivative of del u with respect to del t when the volume is kept constant. Okay, so it means that del u, the change of internal energy at constant volume, is equal to the Cv into the integration of, with a certain limits, the initial temperature being T1 and the final temperature being T2, and it will be dt. So if Cv is a function of t, then you cannot do this operation. You have to understand that Cv and dt will be multiplied and then it needs to be integrated. So depending on the equation, if Cv is a function of temperature, then you cannot perform this operation. I have already assumed that Cv is a constant, so this is why I have separated from it. Okay, so and we know we have dealt with this equation just a moment earlier when while describing enthalpy du plus pdv. That means it is a process where except pdv work there is no other work transfer going on. Now if we keep the pressure constant, then what will happen? This dp will become 0. So that means this part will be removed. So the equation will only depend on the change of du. So heat transferred at constant volume is nothing but du. So we can write this equation as this dq, or specifically heat transferred at constant volume, which is equal to T1 to T2 Cv dt. Okay, so this equation can be defined by the help of. Now heat transferred at constant volume always increases the internal energy of the system, as we have already proved in the while defining the first law of thermodynamics. If the volume is kept constant, then the pdv part vanishes. So it is only the equation is only left with du, and it is quite evident from this equation that if heat is provided, then it is only used to increase up the internal energy. Now, what I am trying to say is that if the specific heat is described in the terms of this heat transfer, then we would like to describe Cv as equal to del Q del T at, so let me rewrite this, del Q del T at constant volume. Now, since you know that Q is a path function, Q is not a property, so you cannot um, define or do a proper derivation or differentiation of this function. So since Q is not a property, this definition doesn't imply that Cv is a property of the substance. So the appropriate way of defining Cv is this, because we know that dq dq at constant volume dq at constant volume is nothing but du. So this is why this here dq at constant volume is not referred, but du at constant uh, volume is referred. Similarly, we can define Cp as the change of enthalpy with respect to the temperature at constant pressure. So Cp will be written as del H del P at constant pressure. Okay, so the specific heat of a substance in constant pressure is defined the change of enthalpy with respect to the temperature when the pressure is kept constant. So we have already defined that del Q at sorry dq at constant pressure is dH. So the heat transferred at constant pressure is nothing but enthalpy. So we know this fact, and we can easily say, combining these two equations, we know that H will be equal to Cp into dt. Okay, just so dH will be equal to, it can be written as Cp into dt from the limits, from the temperature limits T1 to T2. That means from the initial temperature to the final temperature. So Cp is also a property and Cv is also property, but we do not refer this Cp in terms of the dQp, since Q is not a property. Since heat transfer is not a property of the system, we do not refer Cv and Cp in terms of dq. We always try to express these specific heats in terms of enthalpy and internal energy. So Cv is del U del T at constant volume, and Cp is equal to del H del T. So remember this H which we have referred, it is not the total enthalpy, so better it is better that we'll follow the same. So as you can see that Cp has been expressed the rate of the change of enthalpy with respect to the temperature at constant pressure. So one might get confused here regarding this capital H. So I must mention that this should be expressed in terms of specific enthalpy. So the rate of so the change of specific enthalpy with respect to the temperature when the pressure is kept constant is called as the specific heat at constant pressure, and Cv can be expressed as the change of internal energy with respect to the temperature and the volume is kept constant. So these two specific heat constants will be used very much by our different thermodynamic equations. We'll find the application of these two constant in different thermodynamic processes. So I hope that we have done you have discussed a lot of concept over here. Now let us try to solve a problem which I hope will clear your concept in a much better way. So let us read a problem here. The stationary mass of gas is compressed, sorry, to be compressed without friction from an initial state of 0.3 meter cube and 0.105 megapascal to a final state of 0.15 meter cube and 0.105 megapascal. The pressure remaining constant through the process. So this is an isobaric process. The pressure is remaining constant here. So this is an isobaric process. Okay, now there is a transfer of 37.6 kilojoule of heat flow into the from the gas. So there is a heat transfer of 37.6 kilojoule of heat flow from the gas during the process. Now what does it mean? So we are taking the gas as a system. So there is a transfer of this amount of heat from the gas. So this dq should be written as minus 37.6 kilojoule, since heat is going out from the system. So heat is flowing out from the system. So there is a minus given here. Now we need to calculate the internal energy change. So for an isobaric process, we know the work done, we know the formula, integrating PdV, or simply using the formula of constant into V2 minus V1. So this is the most simple formula of work done. We will find the net work done is, the net work done becomes minus 15.75 kilojoule. Now I hope you've understood the pressure is 0.105 megapascal, which is remaining constant. Okay, the initial volume is 0.3 meter cube and the final volume is 0.15 meter cube. So this is a compression process, since the volume is changing in a negative way. That means the volume is decreasing. So ultimately we can calculate the dW, or the work transfer, as this. So we know the first law of thermodynamics, dq is equal to du plus dw. So this is our statement for the first law. So if we put this dq and dw, we will simply get du as minus 21.85 kilojoules. That means the internal energy of the gas is getting decreased by this amount. Okay, so this is very simple problem. So the heat transfer was given to you. You just had to understand it is a negative heat transfer or positive heat transfer. You know that if there is heat flow going out from the system to the surroundings, then it will be treated as negative, and if there is work transfer on the system by the surroundings, it will be treated as negative work. So both negative heat transfer and negative work transfer were involved here, that which followed an isobaric process. We know the formula of work done in isobaric process. We know the formula of displacement work done, right? So which follows pdv. We know p remains constant, so dv is nothing but the change of volume from the limits of v1 to v2. So from this basic understanding, we can easily calculate this formula and we can calculate the work done. Then simply using the statement for first law, we calculate this du, the change of internal energy, and we find that regarding this compression process, the internal energy of the gas has been decreased by 21.85 kilojoule. So this was a very simple problem.
So till now we have discussed the first law of thermodynamics in a broader aspect. Now I would like to do a summarize kind of thing. I would like to summarize the discussions. So you must have understood that this is the basic statement of first law, and when it is mentioned that the closed system is transferring displacement work only, then this formula is used. Okay. Now here, if you see and concentrate on these two energy quantities, you must understand or you must realize that these two quantities are different from this energy quantity. Okay, so these three are energy quantities, but you must understand that these quantities and these quantities, they are the form of energy in transit. Okay, so this energy always crosses the boundaries. Okay, so whenever there is some kind of temperature difference, heat is transferred from system to surroundings, or the opposite may happen. Okay, so they are the energy which are moving through the boundaries, so they are called as energy in transit, whereas this refers to the energy in transit. Okay, so I think you must understand the two distinct natures of energy which is given by the first law of thermodynamics. So this is a fantastic thing where you can see that energy enjoys two distinct categories at the same law. Okay, so this should be understood very clearly. Okay, and you must have understood that the heat transferred at constant pressure is nothing but the enthalpy. Okay, and you must have understood that for the system which is undergoing a thermodynamic process, or we can say a system which is undergoing a thermodynamic cycle, for the cyclic processes, the change of internal energy is always zero. Okay, so this thing should be remembered. Now the question is why? Because internal energy is a point function and it depends on the state, and the most important thing is that this internal energy is a property of the system. So here another point is adding on. So energy is considered as a property here, where this energy is not considered as the point function. They are path functions. So you can see the differences in energy in the single law. You must understand that they are different, and you must understand these differences. Okay, and now for a system which is undergoing a thermodynamic cycle, you can always remember that the summation of all heat transfers should equal to the summation of all work transfers. Okay, so with this understanding, I believe that your concept is very much cleared, and now we can end this lecture. So thank you, thank you for your concentration, and we'll see the first law applied to the flow processes, or the first law applied for the open systems, in the next class. So till then, goodbye and thank you.